I think that
Yeah.
what I've always appreciated about you, Scott, is that your goal hasn't been to tell people things are black and white. More or less, though, you're exposing the shades of gray so that we can think for ourselves. And that's what we really need to do, is we need to spend more time thinking for ourselves than, I don't know who's saying that out there, but I can just picture somebody on a 30-second Instagram reel saying that, rat studies are useless. And then from there, 1,000 people just repeat that and repeat that and repeat that. Let's look at it today. What are the benefits? But then at the same time, what are the drawbacks too? What's up, guys? Welcome back to Muscle Minds with Scott Stevenson. I'm Scott McNally, and welcome to the new year. This is our first episode of Muscle Minds this year. I'm excited to get this thing rolling. Back in the past, like last year, it was actually the last episode a week or so ago, we talked about potential benefits of melatonin, and there was a lot of really cool stuff with that. And I heard some feedback from two people, and it's something that I had heard before. It was said, rat studies don't mean anything. Rat studies are garbage. They don't mean anything. And I thought to myself, I don't think that they're complete garbage. I understand they aren't identical to a human study. But that said, Scott and I have been talking about it, and we thought this would be a really good topic in itself. Who better to explain this than Scott Stevenson? What's up, man?
Not much, dude. Yeah, this is one of those things. I kind of had to make a call at the beginning. You could go. You could teach. I was telling Nick Ware. I think that's why I mentioned this too. Maybe it was you. You could teach an entire graduate class on this topic.
Okay.
Like, it's an important topic. For instance, in my academic career, when I was going through school, I started off doing animal work. So I did for a year and a half, 2 years almost. I did research with rats. And but I wanted to work with humans. I'm too much of an animal lover. I just couldn't bring myself to, because you lose animals sometimes inadvertently, and then they have to be sacrificed at the end and that kind of thing. It's just
for sure
I could do. Yeah, but you see, especially in the exercise science world, there are many, many departments where you have individuals who are like you in the same department. You've got basically colleagues functioning on the same level: animal research, rat research. It was literally that way at University of Texas.
Yeah.
At University of Georgia, there wasn't anyone doing any animal research, but at Texas, there certainly was. So I was in a guy named Roger Fair's lab. This John Ivey, people might know about John. He wrote one of the first carbohydrate timing or the nutrient timing books years ago. He's now retired, professor emeritus at University of Texas at Austin. Great guy. He was the second on my master's thesis. He did both animal research and rat research, mainly rats and mice, depending on which model made the most sense, and humans. And there was another guy who, by the name of Dr. Starnes, he just did all rat stuff, basically, with hearts. So, but there's something to that. So you see this, and the question that's important to understand are what are the limitations, the positive, the advantages. So you could literally do an entire class. This topic comes up over and over and over again, but the bottom thing I'm going to kind of go into is sort of help folks who don't have research training, who haven't done research, who haven't been in that kind of situation, help them a little bit kind of contextualize that there is a reason why for centuries there have been literally millions of researchers who've used animal models for various reasons to study various phenomena in mammals, and then use that as a step to understanding what happens in humans.
Sure.
There's just some stuff you can't do in rats. So to make the statement, one statement, you may even talk with someone else, one statement that I saw was rats don't carry over to humans. It was just simply that, right? Yeah. So a very sort of blanket statement. And it's kind of like saying, and nowadays, if you really want to get somewhere more quickly, you would have an automobile or some sort of motorized means of transportation. And it's like saying bicycles are worthless.
Yeah.
Like, there's no need whatsoever to ever have a bicycle. There's no purpose whatsoever. Like, what if you want to exercise? What if you're just going a short way? People use bicycles all over the world in other countries, in other cultures, right?
Yeah.
Where they don't have to go very far. There are people, like, even in like the big cities, there's people who deliver stuff on bicycles because you can get there faster, right? Because of traffic and stuff. So to say like bicycles are useless because you don't have a use for a bicycle or you don't see a use for a bicycle, it's like it's a little too much of a black and white statement, and very, very few things, especially in science, are black and white. So
and that's kind of something you've struck a chord with me too. I feel like that's something I see in our society in general right now, is that a lot of real black and white thinking that, politically, you're either with us or you're against us. You're either pro this or you're anti that. It's like, and the same thing carries over to bodybuilding, that, we've talked 100 times on drugs and stuff, that, there was a time that we wanted to just like absolutely annihilate estrogen. All estrogen was bad. And now everybody's saying like, no, leave estrogen. You need it. It's good, but it's good within reason. I think that what I've always appreciated about you, Scott, is that your goal hasn't been to tell people things are black and white. More or less, though, you're exposing the shades of gray so that we can think for ourselves. And that's what we really need to do, is we need to spend more time thinking for ourselves than, I don't know who's saying that out there, but I can just picture somebody on a 30-second Instagram reel saying that, rat studies are useless. And then from there, 1,000 people just repeat that and repeat that and repeat that. Let's look at it today. What are the benefits? But then at the same time, what are the drawbacks too?
Yeah, and the thing that it is convenient. It's easier just to compartmentalize things and say it's this or that. Right? Yeah, you go in there's just two boxes. There's no intermediate potential forms of utility for rat studies, let's say. And that's nice because you don't have to think. Then you don't have to contextualize. You don't have to see the nuances. You don't have to see the shades of gray. So it's helpful. It's just a normal human instinct to do that to the extent possible. But then you're overshooting the mark if you just do that all the time.
Yeah.
You just miss so many of the beautiful nuances of life, I think. So
should I bring this up to get us rolling?
Yeah, let's bring it up. I'm going to pull it up on my end.
All right.
I'm sorry if I'm looking up and down because I've got two.
That's all right.
Two screens going here.
We got a lot happening. You think I'll be all right over here in the corner? If you look at us, how I have this set up.
Yeah.
You think it would be okay over here?
Yeah, we may have to move it now and again.
Okay. Well, I'll start us out there then, and I'm going to go ahead and actually, I don't even really need to. I can just go like this. Boom. There we go.
Yeah. There we go. So again, sorry, it's just like the last one. I sort of whipped this together. This isn't, but when I do my seminars, they're paid on location, what have you, or the webinars that I do, I run through them. Literally, I haven't even talked through these slides, so there's probably typos and stuff. So I apologize for that. But and I just came up with the topic. I've actually, I've got it, and I'll show people how to find this. But I wrote an article like almost 10 years ago now on this topic for John Meadows' site. Are you a man or a mouse? And it's about animal models of muscle growth. So I want to sort of focus on that because it's just one sort of sliver of research where you can see, okay, are these studies in this area, in this arena, are they relevant at all? What do they tell us? We could talk about this. You can ask any questions you want if you go along, Scott, because we could talk about each of these slides kind of forever.
All right.
So this was here's a study. Let's see. Make sure. All right, I'm gonna have to use. There we go. I've got. All right. So this is a review article that came out not too long ago, and these are a couple figures I stole just to look at the number of research experiments that are done with animals. And the table on the left is the number of animal procedures in Great Britain in 2018.
Okay.
And so if you look along the species column there, the left, mice, fish, rats, birds, other mammals, reptiles, blah, blah, blah. A total just in Great Britain in 2018 of experimental procedures, 1.8 million, right? So the reason I bring up these numbers is to say these are just experimental procedures. There's other procedures that were done that weren't even experimental. It's just basically developing the models, things that had to be done, which you require approval for. The reason that I mention this is that just make an absolute statement like animal research, that there's no value, that the animal research doesn't carry to humans, is like, so why are we making like 3.5 million mistakes in a year in just Great Britain, right?
Okay, yeah.
So yeah, and it's a massive number of. I mean, we use a lot of rats and mice. Rodents are seen often in exercise physiology. Mice is used a lot because they're really, really small. You don't have to feed them a whole lot. Of course, you can make transgenic mice. You can bring in 100 mice, and they don't require so much space. So really, you don't unlike a fish, they don't have to be underwater, what have you. So it's a really efficient and convenient way of having your subjects all kind of grouped together. So here is another on the. Move myself out of the way here. On the right is another reporting at the USDA from 2008 to 2017 of animal usage in research studies. Same kind of thing. We're seeing like 1 million studies here in 2008. A little bit less actually. Animal research has kind of gone down, which that doesn't bother me one bit. It just means we're probably getting better at determining when we can do animal research, when not. It's a high point in 2010, but we're talking about millions of studies that are going on each year in all these various species. They use cats and dogs, which I hate to see. Yeah. You know, that was one of the things that really got me when I was in Texas. I go to the Animal Research Center there, the Ark, they called it. Yeah. Like Noah's Ark. And I'd see dogs running around in there. That would just destroyed me. So
I bet.
Yeah, it's a big deal. So I'm not like I'm a big proponent of minimizing animal research to the extent possible, but it does have its utility. So let's go to this. So the next slide, get into some of the or bodybuilding related stuff. Look at my screen there. So this is here's some animal models of exercise and resistance overload. I just kind of threw all these together. So sorry for the kind of lack of organization.
That's all right.
So in the upper right, I've got I took from a paper from 2019, a rat running behavior scoring system. So this is the thing that's interesting about rodents. It's a limitation, but it's worth knowing. This happens, I know, in running. This also happens in swimming when they do swimming models with rodents. It's literally potentially a limiting factor, and it's a limitation. And maybe even a deficiency in this type of research is that you can only train the animals that want to run. So you can score some animals, and this is even in animals that come from the same litter of rodents, let's say. Mm-hmm. And some of them want to run and some of them don't. And the way the rodent training happens is typically the treadmill that's got a shock grid at the one end. So you put them on the treadmill, and they quickly learn that if they don't run, they will get shocked. Some animals just would rather be shocked. So they literally just say, I'm not running. They just go and they jump on the shock grid. They just,
no kidding.
And you try to train them not to do that. But some of them will just want to do this. Huh. So you can see like there's a non-runner. They'll refuse to run. They freeze on the treadmill or they're on the shock grid. I'm reading from the bottom here of score number 5. And they get removed from the study.
Okay.
With swimming, sometimes you put animals in like a barrel, a big pail. Yeah. And some rodents will swim around. And that's the idea, is they kind of doggy paddle their way around. And those are good swimmers. Mm-hmm. And some of them will figure out, they're like, because of course they're scared of it. There's a human on the surface, just like a frog would, a frog or something in some amphibian. You come up to them and they dive bomb. They go under, right? Well, yeah. Rats will do that. Some rats will do that. And they'll just go to the bottom of the barrel and they'll just sit. Hold their breath as long as they can, and they come back up to the surface, and they'll take some breaths, and like, oh, there you are again, shit, and they go down, they swim down to the bottom, and they just sit there, yeah, right. So they're not swimming. I mean, that's a stress, yeah, but it's not a swimming stress. It's not an exercise stress that we're looking for. It's a stress on their cardiovascular system, et cetera, et cetera. So those are the non-swimmers. So that's, for instance, something that happens with running. It happens in some of these other studies, in various degrees, but like the one just below to the right there's a raft cat press. Yeah, calf press. That's pretty interesting. Yeah, there's been a couple of these. Sometimes they can load weights on rats and train them to climb ladders. So they're literally climbing up ladders with loaded vests on. And this one you can see you guys can't probably see. I think you can. Let me do this here. Get out my little pen. And you can see there's a little ring that goes around his neck. And this is a feeding tube. So there's little food pellets in there. Okay. So he has to stand up and extend his legs. So he trains the plantar flexors, the calves, and they have a little weight connected to this ring around his neck so that his shoulders press on that. So it's kind of like he's doing a standing calf press with the weight on his shoulders. Yeah. And that weight loads him. So you can do progressive overload in this weight. So they get their feeding only if they this is the ultimate like food reward, right?
Yeah,
Because they have to train themselves. They have to produce effort, and you can train that way with a food reward.
Yeah.
Here's a system with rodents that is an interesting. We use e-stimulation. I actually developed this system when I was in Texas. I wrote the software.
Really?
Created the apparatus using a solenoid. Yeah, I just had to figure it all out from scratch. And we did something a little bit different. We actually implanted a headgear here and ran a wire down to the tibial nerve. And then you strap the animal's foot to do a unilateral calf press on this kind of a pulley system. So that when they plantar flex, this thing rotates and that lifts up this weight and that loads the calf then. And you can do progressive overload. We talked about this in a previous podcast. I think that was maybe in one of those like 100 to 102.
We did
podcast studies worth knowing. Yeah,
we've talked about it more than just that one time, but I had never seen the picture, the little diagram until right now.
Yeah. So it's a cool model. Mine was a little different, but it's based on this. The cool thing when you activate with e-stim, literally, so the animals were anesthetized; they're unconscious when they're doing their training. So you just use e-stim. You turn on the tibial nerve that turns on both the anterior tibialis as well as all the plantar flexors, the gastrocnemius, the soleus, and the plantaris. So all those muscles get trained and they lift and lower the load, right? Not so much lowering; it's mainly concentric. You just turn it on and they do the plantar flexion, you turn it off, and then it just comes back. But what happens, because all those plantar flexors are stronger than the anterior tibialis in the front, that muscle gets turned on, the anterior tib, and undergoes an eccentric contraction.
Yeah, okay.
For each of those, because it just gets stretched while it's contracting. And you get increased protein synthesis there, you get massive growth that way too. So it's just another animal model that's interesting. Here's some other, and kind of the point here to keep in mind is that the reason why these things were done, and they have been done. And here's another cool one. People talk about the possibility of hyperplasia. So here's the closest thing. This is a training study that was done with cats. Bill Gagne and Jose Antonio did this. Jose Antonio is still active. People who know ISSN know Jose. He kind of runs the show over there, and he's written some cool stuff on actually changing the shape of muscle, and a really cool article on hyperplasia, which most probably happens in humans. But the problem with, of course, trying to figure that out in humans is you can't probably ethically, at least, take out a muscle and count the fibers, which is something you could do ethically, so to speak, in cats or in rats or in quail. So in this particular study, they train these cats to do wrist flexion against the load. So there's a pulley system here. You can see the loads over here. So they would do a wrist flexion against this pulley system for a food reward. In this case, they found after a year of training, there was like a 9% increase in fiber number in the flexor carpi ulnaris muscle, so one of the wrist flexor muscles in the forearm. The other study, and this is one that people have talked. Dante Trudel talked a bit. This is the stretch overload model with quail.
Yes.
In this particular way they did it, Gagne did a lot of these. They put this cuff around the wing, and that's covered up. But this is a weighted cuff, so they can increase the weight on this cuff, and this pulls the wing down. I always talked about the equivalent in a human would be like holding a heavy dumbbell, like strapping a dumbbell to your hand. So you're holding like a 40, 50, 60-pound dumbbell all day long, and it's just pulling your arm down. And they measure the anterior latissimus dorsi muscle, but it's basically equivalent to looking at the upper part of the trap, right?
Okay, yeah.
And see how much your traps grow. And that's the study Jose did. He did a progressive overload study, giving the animals a break in between days when they would progressively add weight. And he saw it was like a 300% increase in muscle mass in the course of 1 month.
Wow.
It's ridiculous. Yeah. An increase in number of fiber. And this was this cool study where the fibers, initially the increase in muscle mass. So they had cohorts of animals, thing you can't do in humans. So the first group got trained for a week, and they looked at the muscles, what happened to the weight of that muscle, the fiber sizes. And then the next group was trained 2 weeks. That's when they ended their training, so to speak. And then went to 3 weeks and 4 weeks. So they could see what was happening to both the muscle weight over time and the fiber size over time.
Yeah.
And the muscle weight, so the muscle mass, kept on growing over the course of the month. The fiber size initially was producing that growth. And then later on, in the latter half of the study, the fibers started getting smaller. And And this is what you see in some human studies where you have humans that are bodybuilders that have large muscles, but they have normal fiber sizes, which probably reflects what we saw happening in this animal study, which you can't do that in humans. Just let's take the humans and you're going to train your triceps, let's say, and who wants to be you're going to get randomly assigned to the group who loses his triceps after 1 month of training.
Yeah.
So we can count the fibers, and it just doesn't happen. But this stuff that animal models will allow us to do, and it's important, I think, to recognize this gives us insight as to what might be going on. It gives us some evidence to support the assertion that when we see large muscles in bodybuilders who've been training for years, who have normally sized fibers, that probably has to do with what we saw in this quail study, where the muscle kept on growing, but the fibers got bigger and then got smaller, so there's more fibers. You can't have fibers that are getting smaller and muscles getting bigger unless the number of fibers is getting bigger. Yeah. Right? And there wasn't more water, there wasn't swelling, that sort of thing. That actually goes down after the first little while of the training or of the stimulus. So it tells us that that's an adaptation, and I've explained this in previous podcasts, that would make sense when we think about what muscle has to do energetically when it's undergoing a high volume resistance training test, which is kind of like this is a 24/7 stress for these birds, constant being stressed. So that's this quail study, and that you see massive, massive growth here. It's way beyond what we would ever do in a human. Yeah. But we see a phenomenon there that matches what we've seen in cross-sectional studies with humans, bodybuilders with big muscles and average-sized fibers versus untrained people who have smaller muscles but the same size fibers. Yeah. Those bodybuilders probably didn't start off with really small fibers, and they spent 10 years training to make their muscles larger than average by 50%, and their fibers average size. Yeah. They probably got some muscle growth in the fibers, some hypertrophy, technically speaking, in the fibers grew. And then over the course of time, the continued growth they got was likely due to hyperplasia.
Yeah, that makes sense.
You can measure that directly, yeah. So this last one here is a compensatory hypertrophy, synergistic ablation, they call it too. So here we got the gastrocnemius, the soleus, and the plantaris. So humans have a plantaris. Not everyone does, but it's really small if you do. Sometimes people have it on one leg, not on the other. But the main calf muscle is the gastroc and the soleus. But in rats, we've got this plantaris. So you can take out the gastroc and leave the soleus and plantaris left over, or you can take both the soleus and gastroc out and just take the plantaris. The interesting thing about the plantaris is it's a mixed muscle fiber type. So you can look at the importance or the differences in terms of fiber type on the growth response. The soleus is in a rat is 90% type 1. Hardly a muscle in humans that's like that.
Really?
I mean, there will be individuals. Yeah, there'll be individuals who are very endurance. They're gifted for endurance running. You'll see this. Yeah. And typically, those biopsies are taken after they've also been doing endurance training for a long time. But having more type 1 fibers is going to give you a greater propensity for being good in endurance type training. But in rodents, we see this, especially in rats. That the gastroc, there's two heads of the gastroc, and they differ a little bit in terms of their fiber type percentage. Red versus white comes from a whole notion, some background information. So people talk still about red versus white fibers, right? Or red muscle versus white muscle. Well, the soleus is a very red muscle because it's got lots of myoglobin in it. It's got lots of capillaries, so it's going to be a lot of blood if you take that muscle out and look at it. Whereas you've actually got a white and a red gastrocnemius. You can see visibly if you strip away the skin, you look at those muscles, the two heads of that muscle in a rat, one is white and one is red. It's kind of a pinkish and a more whitish color. So that's where that nomenclature comes from. Originally was from the rodent research. Before, you can't take the whole muscle out in human. When a rat, you can. You can take it out and weigh it, and you can analyze and count the number of fibers to look at the possibility for hyperplasia. Yeah. And you've got these kind of cool situations where you've got muscles that are almost all of one fiber type. So you can see how things differ there. You had a question, I think. You're going to say something to interrupt?
No.
Okay.
I just said, yeah, so I was just kind of listening along.
Yeah. So this is a chart from a nice review. It's a bit old, but these models been used. This was in 1990 when this publication came out. So more than 30 years ago, and these models have been used for decades before that.
Yeah.
So they kind of compared strength training versus the stretch hypertrophy, which is the quails, to compensatory hypertrophy or synergistic ablation, to exercise-induced models like this or this one. This one's a little bit different because these aren't voluntary contractions. And you see in terms of he calls it the response topography here, that you see the same sort of adaptations in these animal models in terms of fiber type changes, in terms of the relative amount of growth that you see in humans. So you're getting a similar type of effect. You're not seeing the animals they're getting like 2 or 3 times the muscle growth when they're undergoing the same kind of stimulus. The thing that's interesting is that we can't really do stretch hypertrophy in humans, and when compensatory hypertrophy is compared to resistance exercise in humans, you get a much more robust growth response. So it's pretty tremendous. So 50 to 100% increase in muscle enlargement or muscle mass, just weighing the wet muscle here in this case. Except there's a nifty little study that I know I've mentioned here a couple of times. I think is really cool. So at this point, we didn't have anything that was comparable in humans in terms of compensatory hypertrophy. So this, of course, again, you're taking out the gastroc or the soleus. You're looking at what's left and look at the extent of growth you get in those muscles. Right. About a 50 to 100% growth over the course of months, right? And pretty much after 3 or 4 months, you're getting things that plateaued off. And what's worth knowing, I don't think I mentioned this. What happens in these animals? They cut the insertion connections here. So they cut the Achilles tendon or the large part of it that connects these two muscle heads to the Achilles tendon.
Yeah.
And then the animals recover for a few days, and then they just walk around and they regain normal locomotion. So their activity becomes the same. So the overload isn't from lifting; it's from walking around all the time.
Yeah.
And they just have much less muscle mass, but they have an adaptation that compensates for the missing muscle mass, and they get hypertrophy. They get muscle growth, and so you actually get some hyperplasia there, but they just call it compensatory hypertrophy. So we've got this very cool study that I found a couple of years ago. I was so excited when I found this. So again, the remaining muscle grows 50 to 100% when we do this compensatory hypertrophy, which you're not going to do. You're not going to cut muscles in humans and see what happens to the remaining muscle, like cut your gastroc, see how much your soleus grows.
Yeah.
But people sometimes have Achilles tendon ruptures.
Yes,
right?
They do.
And one way that you can repair that is take the flexor hallucis longus muscle. So that's the muscle that flexes your toe.
Mm-hmm.
So it's a little bitty, normally a little itty muscle here. It's not very big. That comes under your medial malleolus here and goes down to your big toe.
You're kidding me.
Flex your big toe.
Huh.
Yeah.
I never knew that. It's just fascinating that it has that level of circuitry that runs down. I've heard that the foot is the most complex, one of the most complex parts of the body.
Yeah, I mean, the hand is even more complex, but it's important. You kind of run. A lot of the power is developed off the ball of your foot. So this muscle is here to keep your big toe, your hallux, hallucis longus refers. This is just there's the hallucis brevis muscle too. So this is the long of the muscles. So what they do then, in the case where your Achilles, where this muscle has been, where your Achilles has been torn through an accident, right? Mm-hmm. Is they basically they kind of sew this end tendon together, and then they cut the normal attachment here in the hallucis longus, and then they attach that at the Achilles.
Oh.
So basically, what we have is this small muscle that has to take over for this muscle mass, which is now not connected. It is sort of partially, but we've got a very, very similar situation to when you've done the clipping here experimentally, because here we have a situation where there was an injury. So now we got a ton of overload on this flexor hallucis longus muscle. And in this particular study, this was just a follow-up study. And what they did is they compared the good leg. So people didn't have bilateral Achilles tears. There's just one side. So they compared the good leg, and they're walking basically normally. They did some muscle strength tests as well. Kind of bypassed that. Those details aren't really important for this talk, but they found on average when they compared the normal size flexor hallucis longus at its normal size with the one that had been used to compensate for the torn Achilles, about a 52% increase in muscle size.
Okay.
And the max was 104%. And here's an MRI showing this.
Yeah.
And I circled this already. So here's the good side, flexor longus, and here this is a really shoddy circling, but this is how they do this. I did this for my dissertation. You circle the muscle.
Yeah.
The computer will help you make a better circling process. So this was a doubling, a little bit over 100% increase in flexor lucis. So that suggests very, very coolly that at least this model of compensatory hypertrophy in rodents, where we get about 50 to 100%, we've got the same response tomography, as Timpson referred to it. In humans, when we have a similar situation where we have one muscle that has to take over and compensate for missing muscle mass otherwise.
Now, let me ask you a question.
Yeah.
Now, did we do the rat studies first, and that informed us to say, hey, we may be able to do this in humans? Do you know if that's... I would have to think that there was some, they didn't just come up with that one day and say, hey, let's give this a try. I guess my question was, is this based off of having known through studies in animals that this could be something that could benefit us?
Yeah. Well, in the animals, they just cut the muscles. They don't do any tendon transfer.
Okay.
So this is a tendon transfer procedure that, that surgeons figured out and probably could go and look. I haven't looked in that literature. Go and look and see.
I'm just wondering.
You can see her just from.
Yeah, I'm wondering if animal studies had informed us I'm just trying to see, where have animal studies benefited us? Had they benefited us in this case? I see what you're showing us, though. You're basically showing us that this is something that had occurred. A similar type thing was done in animals, and we got a similar result in humans, is what you're telling me.
That's a really good question, because I think. Imagine this. Imagine we do this. We call it compensatory hypertrophy because there is a compensation. But imagine there was no compensation. Imagine what happened was the animals were just permanently debilitated.
Yeah.
Right. And they never recovered. The normal gait was never restored, and you didn't see any growth in the remaining muscle. So you cut the gastroc, and neither the soleus and plantaris can ever take over. It never grows again. Yeah. Or you try cutting the soleus. Like no combination, you see any compensation in terms of muscle growth to make up for the muscle that's been where the tenotomy has occurred, where the tendon's been cut.
Yeah.
Then I almost 100% positive that the smart researchers, because we pay attention to the animal literature, right? They would have said, well, it would probably be a silly thing to try in humans because the animal research suggests there's no compensation. So if we tried this tendon transfer and hope that the flexor lucis longus would then grow, which it does, but the animal research says that the rodents are they're hardier than humans, right?
Yeah,
that's kind of the concern, is that they can handle shit that we can't handle. And that's probably true in some cases. It's just kind of seen. They're just a general observation. They're just pretty hardy. They do stuff. Some of it's I won't even say what it is because it's kind of. But animals will do things that like what's the movie, Scott, where these guys, like, they're on some sort of a flight over Antarctica or and the plane goes down and they end up like becoming cannibals and like eating.
I know what you're talking about. It was like the soccer team or something.
Yeah, something like that. So you're like, holy shit! Like people are crazy. Animals do that kind of stuff. Like,
they adapt.
They're capable of that.
Yeah,
they adapt. Like, and they're willing to do things that we think of as very animalistic. It's kind of where the term comes from.
Yeah.
So they're really friggin' hardy.
Yeah.
So if the research had shown that animals, being as resilient as they are, as hardy as they are, they didn't have compensation to this type of attempts, and I'm guessing the surgeons would have thought, because you have to get these things approved initially in some way, shape, or form. There's research that usually has happened before, unless there was some rogue surgeon. Again, I haven't looked into the origin story of tendon transfers to see what they did, especially in terms of this. This is different than, for instance, the tendon transfer in the hand. Okay, right? Because they do hand tendon transfers too for people who've had injuries from car wrecks or what have you. Yeah. This one's a continuous loading. So if you're going to try to justify this thing and you say, we know that when you do with the compensatory hypertrophy model that animals do compensate when their muscle mass is missing, blah, 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 that gives us reason to believe that there's potential for success in these individuals. if we try this particular tendon transfer, thing I was getting ready to mention is this flexor hallucis longus tendon. It doesn't have to be transplanted very far. It's in very close proximity to where the tendon that is cut or which has been disrupted by the injury is. So it's kind of the logical one to choose because of that.
Yeah, it is.
So
I see that.
Yeah, this is really I'm so glad you asked this, because the animal research informs us that we have some potential success to be had here in trying this tendon transfer procedure, which is now done. I think there was like 8 or 10 subjects, so to speak. This is just sort of a cross-sectional case report, basically.
Yeah.
But yeah, if the animal research suggests that the muscle just doesn't have the plasticity, which we now know it does, then you couldn't have convinced a human subjects committee that this is a viable study to do, because they'd say, no, you're not going to do that. Like, you make them suffer through the study, and then their muscle's never going to recover, and they're just going to be, you're just going to put them through unnecessary pain and suffering.
Yeah, so, I just figured I'd ask that, but yeah. What else we got here?
Great question.
I'm excited to see where we go with this next.
Yeah. Okay, so this is from what I put this together for this article I wrote for John Meadows' site, so people can find this if they go in there and just look at my name. They can. So if we look at animals versus humans, this is sort of a scale of changes in muscle size. Kind of, here's our baseline. You can go atrophy. There's various muscles there. I think these are just muscles of muscle growth we went into. There's muscles of atrophy that humans and animals have, and those are comparable too. And then if we look at what happens in terms of muscle growth on a scale of like 50 to 200, and this would be actually 200+%. We had more than 200% in that one study that Jose Antonio did.
Okay.
We've got sort of this scale where bodybuilding training gives us slow gains, and if you look at someone who starts off at like 160 pounds and they make it to 260 or something like that, they may have doubled their muscle mass, right?
Yeah.
We're in this 50 to 100% range with compensatory hypertrophy with animals, right? Resistance training with animals matches what we see with humans. Right? Resistance training in the short term matches the rate of growth we see in humans. We've got now this cool case study with the tendon transfer, where the compensatory hypertrophy, basically what that was in animals, was equivalent to what you see in humans, 50 to 100%. The numbers matched really, really well. And of course, there's various things that play a role here, and this is important too: supplements, diet, training, and lifestyle, and genetics. I should have probably written this in here, added this. Genetics is huge. I want to make this point too. Looks really good. Looks like a child just scribbled with crayon.
I wasn't going to say anything.
That's okay.
I was going to give you credit for trying. You get credit for trying.
Hey, that's not bad. That's spell with the mouse. This is what happens when you do like electronic signature signing, and you just scribble.
Yeah.
It always looks ridiculous.
Yeah. Redo.
How that can count legally.
I guess this is good enough.
So in e-stim training, you can do e-stim training in both animals and humans. I did this actually for my dissertation. We trained humans with electrostimulation, at least in the short term, like an 8-week window. Okay. You get about double the rate of muscle growth when you train with e-stim.
Damn.
And you get with an isokinetic device, because you're producing a contraction in a way that your nervous system can't. You're overriding the normal neural inhibition during eccentric contractions, and when you're in an isokinetic machine, the muscle forces that eccentric contraction at whatever speed you've set it up to do that.
Yeah. And
there's no inhibition to reduce the force, the amount of muscle that's activated. So the forces are just sky high. They're beyond, they can be depending on how much stim you use, how much juice you have coming out of the machine.
Yeah.
They can be higher than what you can physically produce voluntarily with a maximum voluntary effort. And you're using less muscle to do that because you're not fully turning on the muscle with all the stim. You probably would end up injuring someone if you tried to do that. I've never gone that far, even with myself, because I'm like, nah, that's not smart. That's why the nervous system has this built-in inhibition anyway. But you can get more that way. And this is what's the name of the device? A lot of people were using, especially a couple of years ago. Dexter Jackson used it.
The newbie machine.
The newbie machines, yeah. So that's one form of e-stim training people have been adding. You get a non-physiological e-stim contraction pattern that's going to favor activation of motor units during the eccentric that you might not normally activate, literally maybe at all, with a given free weight. and you create massive amount of muscle damage if you do this without having familiarize the muscle to that, so you get sort of a repeated bout effect. You can destroy the muscle with e-stim, really damaging. So that tells you how novel and powerful the stimulus is. So e-stim training, that's a whole other topic worth going into. But the main point here is that this animal research, all this stuff matches really well. We have a response topography that's really, really similar to humans. So there's something to say there for using animals where you can take out the whole muscle and you can count the fibers and you can do things that you just can't do in humans.
Yeah.
And there's other advantages there too, which I'll talk about a bit too. So more on animal models. People want to read this. Are you a man or a mouse? This article that I wrote back in 2013 for John, and this is where this figure comes from.
Great site.
He gave me permission. Awesome site. Still great stuff on
I had signed up there to get
too.
your How to Skin a Bodybuilder articles, part 1 and 2.
Yeah. Yep. I've got I think 13, 14 articles on there. That's where the L-carnitine article is too.
Oh, yeah.
That Monster 2-parter not long ago, just this last year in 2022. So a little bit more. I thought about, do I want to open the can of drugs? Because I think we both were saying that this idea that rats don't apply to humans, or animals don't apply to humans. There are some differences. So this is a really cool figure. This comes from a publication by Shanks et al. 2009. They credit James Harris for this, so you can find this figure there in this. If everyone wants the original studies, I can send those to you. I rarely get asked for those. Every once in a while, someone asks for a study, and it wasn't actually a study I was talking about. It was a hypothetical, but if you want these, I can always send these. So this is a pretty cool figure that's really, really interesting. And this is looking at bioavailability. And so here is the animal bioavailability from 0 to 100% for various drugs that were under study compared to human bioavailability. Okay. And they just grouped this into primates, so monkeys, macaques, that kind of thing, rodents, mainly mice and rats. I have to throw hamsters in there, and then dogs. And if there was equivalent bioavailability, so that's really important for a drug, right? Take 100 milligrams, how much of it actually is bioavailable to have its pharmacodynamic actions. Yeah. We're talking about one aspect of pharmacokinetics, what the body does with the drug. And if it's a 1-to-1, 100% for both, we would be up here. 100% for the rodent. In this case, I'm circling a green one, so that's rodents. 100% for humans. And then the line of identity would be here, be a straight line. And for some drugs, this could be maybe where curcumin is, if it hasn't been modified in some way. Curcumin is very poorly bioavailable in terms of what gets into the bloodstream, although it probably has some of its actions on the microbiome. So we've got, for some drugs, a very similar bioavailability, right? We look at those that are sort of centered around this line of identity. But then you're going to have some drugs, like this one, where it was 80+% bioavailable in humans on average, and then in rodents, it's 2% bioavailable. Nothing, right? And sometimes it can be the opposite. So that's the thing that needs to be examined. When we have a rodent study, and sometimes people don't look at these. Even this can be a tough part. Sometimes it's happened with the melatonin topic, for instance. I noticed that it seemed like a lot of reviews were picking up on and discussing important points that I saw discussed in other reviews. Okay. How come they're not mentioning this? So people aren't going back and doing the full review. And what ends up happening with a topic like that's been discussed ad nauseum. And I see this. I see even sometimes students being taught this in universities, that old studies that are older than 5 years, you can't cite those for a review article.
Oh, really?
Like when you write something, yeah. Not at all. Even if you want to provide historical perspective, they just don't want any references. Just you have to ignore the past.
Huh. Okay. Basically.
And that is a fatal flaw, as far as I'm concerned. Because what I think happens in looking at just this phenomenon where reviews seem to miss what other reviews have caught on, is if you don't go back and look at what has previously been done, then you're missing some very important very important factors.
Yeah.
And literally, like, very basic phenomena cannot be picked up on. So, so that was, we talked about that with melatonin. So this is just one feature where sometimes it is and sometimes it's not. So if you want to say that someone could look at this and say, well, look, there's really no correlation here, right? That's, if you correlated all of these points, it's just basically a random scatter. There's no clustering of these points around this line of identity, which suggests that there's a Pearson product moment or other correlation between the animal bioavailability of all these different species and the human bioavailability. So someone could say then, there's no application in terms of bioavailability. We can't count on animal data whatsoever to reflect human data.
Yeah.
Because looking at as the whole, that's true. If you look at this particular statistic, but I refer people to look up the book, How to Lie with Statistics. This is one way you can lie with statistics. There's a whole book. That's the title of the book. But in some cases, for some drugs, you've got very, very similar bioavailability. In those cases, then the animal data is very relevant. So let's go back here to even this quail idea. It's like you can't do this. And the extent of hypertrophy and muscle growth, here's the stretch overload, right?
Right.
You get like 200% increase in muscle size in a matter of months. There's nothing you can do with humans that you could get approval for that would do that. And who knows? Probably too with humans, because you really just have your clavicle connecting your shoulder girdle to your spinal column. It's actually your rib cage, right? You probably would like end up like dislocating or subluxing your spine and or separating your shoulder if you tried to like lug a 50 or 60 pound dumbbell around for a couple months, like constantly hanging.
Yeah.
Like even you're sitting at your desk, like you got to type with one hand because that thing's constantly hanging with these birds. So you just couldn't do that. But what we did get, as I noted with this, that I talked about the study with Jose Antonio, we had this really cool phenomenon where the fibers got bigger as the muscle got bigger and the fibers got smaller as the muscle continued to grow. That explains something we see in humans where we can't take out muscles and we can't count all the fibers, where we see humans with big muscles and average size fibers. Maybe the same thing happens in humans. So even you look at this one aspect, this one feature of response topography where you've got muscle growth that way exceeds anything we've seen in humans, there still was a phenomenology behind that where the fibers got bigger and they got smaller as the adaptation proceeded over time that explains something when we look cross-sectionally at bodybuilders with average size fibers and big muscles. So if you're throwing the baby out with the bathwater, if you just generalize in that way. And those are some examples from the area of exercise science and muscle biology, muscle physiology, and bodybuilding, basically, that are pretty cool. What do I got now? Oh, here's another people. I just kind of refer people. This is the title of a paper that I thought was pretty cool. So there's some problems too. If you look at systematic reviews, so this is sort of review of reviews, that can be issues that you've got some advantages, and I'm sort of going to kind of generalize. It's a huge review. You've got some advantages, which you talked about with the animals. But sometimes that leads to a little bit of sloppiness in terms of how the science gets done. One thing I noticed just in, and you can see this across science, is that the harder the science, let's say, so physics is a very hard science, right? Either the particle exists or it doesn't. Either you measured it or it didn't. And if you're talking about like particle physics, like a photon's a photon's a photon. Like, that's not true of humans. Like, a human's not a human is not a human. We've got massive bio individuality here, whereas in physics, which is kind of the hardest of all sciences, they don't even worry about statistics. Lots of cases, right? Because they don't need to, unless you're getting into, if you're getting into all sorts of theoretical physics, then you've got a different story. But for instance, one of the things was brought up, if you look at toxicology, the way that animals handle particular toxins compared to humans, it can be very, very species specific. So rodents, for instance, they can handle a lot more toxins, even when you relativize it to body surface area, which I didn't mention. I should have thrown that in here. But You can find that. I've mentioned this repeatedly over and over again. You just can't say if you give 1 gram per kilogram to a rodent, that's the same as 1 gram per kilogram for a human, because metabolism varies. Typically, people use body surface area because there's a relationship between body surface area, which reflects size, but not just mass, and a rate of metabolism. So there are ratios that can be used for comparing mice versus rats versus humans, or hamsters versus humans, or dogs versus humans. So in dogs, even when you do that relativization, toxicology can be very, very different, right? Experimental conditions in humans can kind of distort the outcomes. So you can use really high doses. You can do things that just wouldn't be ethical.
Sure.
In humans, they don't mimic the human scenario. So, you overload a rat and feed them what would be the equivalent of 1 pound of some supplement per day, and they get cancer after a year. It's like, yeah, but no one's going to eat 1 pound of caffeine a day,
right.
or 500 milligrams of caffeine a day. So it's nice in that you're getting in an extreme circumstance. We push this to the very limit, and these animals end up with this toxicological profile. Mm-hmm. But it really doesn't have relevance to what the average person is going to do. But it's a nice thing to know. It's not a benign substance. There are some side effects, toxicological issues. Yeah. Thing I mentioned before, methodological quality, so sample size. Like in a human study, you need to do what's called a power analysis. So you figure out, okay, what is a meaningful difference when we have X condition for one group versus the placebo group or the control group?
Right.
Is 20% more muscle mass or 50% more muscle mass important? Okay, cool. So if you want to have just a relatively good chance, and there's sort of numbers that you can use that are sort of agreed upon, of detecting such a difference in your experiment, then you need to factor in how variable the response is, so the standard deviation of response, and also how robust your response is. So you want to have, for instance, a training protocol that produces muscle growth in the first place, right? So if you want to see something that would potentially increase muscle growth, then you have to have something that produces muscle growth, right? So that has to be factored in, and you can run this basic power analysis. It's a very simple thing to do, really, if you have data from having done these procedures in your lab. And then you say, okay, I don't want to have an underpowered study, so I need to have 20 people in my study because we have massive variability and we don't have a great training response, which is the problem, for instance, with trained individuals. So we're going to have to have a long study, a 6-month long study in trained individuals who have at least a year worth of training, let's say, which is kind of a common starting point. We're going to have a huge study. Is that feasible? Yeah. On the other hand, when you've got animals, what kind of happens is they're all from the same litter. They're very, very genetically homogeneous. They all look the same. They actually do have personalities to some degree. Like people who work with rats, they kind of get to know which one's which. Yeah. Give them names sometimes, that sort of thing. But they're very, very similar. So they're like family members or even closer. Right? And they're all the same sex. You don't have gender or sex issues. And you can control their conditions, you control their feed, you control everything that's going on, especially in terms of what condition they get, whether they're the trained group or the non-trained group, or they get the supplement, don't get the supplement, or what have you. So what that means, of course, is that that's really, really powerful because you don't have a huge variability. And if you can do things with animals that like compensatory hypertrophy, you get this robust response. You get 100% muscle growth in a matter of a couple of months. That's awesome. Yeah. So then you can see if something matters. You do run into a potential ceiling effect. Maybe you're turning on muscle mass, muscle growth so tremendously, it doesn't matter what you do, right? It's going to happen. And that actually does. And I'll come back to that in just a second. So in animal research, sometimes what happens is they don't do power analyses. They're like, why would they need to? They know they have a robust response. They know they have minimal variability. They got all the features they need to be able to pick up on things. So they do 6 animals, or they do 10 animals. a lot of good studies, they do money more, but that tends to be an issue because animal researchers, they don't do that necessarily because they've been, for instance, doing studies where they didn't have to do it and get away with it. So what ends up happening is they have underpowered studies. If someone goes back, this is what this researcher did. They went back and looked and said, yeah, well, you didn't find a difference because you had an underpowered study. You didn't have enough samples. It would be like going out and saying, I want to find out if men are on average taller than women.
Okay.
And you just go out and you look at the people who happen to walk past your driveway, right?
Yeah.
And you pick 2 women and 2 men. And you end up picking two short guys and 2 tall women. Like, okay, there we go. Women are taller than men, right?
Yeah. Yeah.
Well, on average, it's not true. But your sample size wasn't big enough, right? And you had too much variability because there's going to be lots of women that are taller than men. There's lots of overlap. So, interestingly enough, I was going to say in the context of compensatory hypertrophy, which is very interesting, and I've mentioned this before on the podcast, it is a very robust response. Yeah. And you can look up a guy named Goldberg. We talked about this, I think, in the previous podcast.
We've talked about Goldberg.
Literally, you take out you streptozotocin and you kill off the beta cells in the pancreas, so there's no insulin.
Yeah.
The muscle grows just the same, compensatory hypertrophy. You take out their thyroid gland. You got no thyroid. It's important for metabolism, right? Right. Doesn't matter. You get the same rate of muscle growth. You take out the pituitary. So now they're missing thyroid. Now they're missing growth hormone. Now they're missing testosterone. You got the same rate of muscle growth. It doesn't matter. You take out all those things. You take out the thyroid. You take out insulin. You take out growth hormone. You take out testosterone. Kind of important from a bodybuilding perspective. And the muscle still grows just the same. Because, and of course, we don't have. They don't have the tendon transfer studies in humans where they found some people who were missing their pituitaries and they took them off their thyroid medication and they gave them diabetes and let them go without insulin. But you can do this with animals and you see their same rate of muscle growth. So that's an interesting factor, right? If you look at that, you'd say, well, insulin doesn't matter for muscle growth, which we know from tons of other things. Testosterone doesn't matter for muscle growth. Yes, it does. We know this, right? You look at the other studies, but if you look at that body of literature, those things, you're like, okay, this animal model, it sucks. Like, it doesn't tell us shit because it doesn't tell us about those important hormonal factors that are important for muscle growth.
Yeah.
Well, don't throw the baby out with bathwater. It is important because it actually matches in terms of the response, in terms of muscle growth over time. It does match really well with humans. We know this from the tendon transfer thing. So there's things to take, but you just have to take it with a grain of salt, the appropriately sized grain of salt.
Yeah.
So, and then the last thing, I think I mentioned this in maybe the next slide. You can come up with transgenic animals. You've got this genetic homogeneity. So you can make animals, like animal models of obesity where they're missing the leptin gene or they're missing the gene or they have a defective gene for the leptin receptor. Right. And those, they're just, so you've got some people, there's like I think a family that was from France that lacked the leptin receptor and they were very obese. But, if you really want to say, okay, is leptin important for this, that, or the other? Just use a transgenic model. Like you completely wipe the impact of leptin.
Yeah.
Well, you can't do that in humans, right? You can't, you're not going to find people to do those sorts of things. Someone who if someone did lack in leptin and you knew this, well, then the ethical thing would be to start treating that lack of leptin for their own health purposes, right?
Right. Right.
Yeah. So on the other side, you've got this human genetic diversity. So there's an advantage there, and you can have a very detailed, like sort of non-physiological, pathological way of observing the impact of specific genes or specific hormones or specific proteins on any type of physiological response or adaptation. And then you can take some information for that, but no, it doesn't. You can't say that, leptin is all that matters for human obesity. That's of course not true. But you do know that if leptin isn't working, those animals are very obese. They're just round balls of fat, basically.
Yeah.
Both the OB, and the DB mice. So, a couple last things, general thoughts. I've mentioned this already. Animals are, the inbred species with genetic. Sorry about the spelling issue there. Just typed this up like an hour ago. And we get wide genetic variability in humans. This is worth knowing too, or mentioning. There's a hierarchy of scientific evidence. So, you can have case reports, individual observations that, you'll see, which can be very, very valuable. This is where some people would put, bro science to some degree, or bro anecdotal reports, right?
Okay.
This is what I see. When I think of bro science, I think of something where someone has said, this is what I see, and here's my scientific explanation for it, and the science is just completely made up. It doesn't match anything that's actually scientific. It doesn't match anything you learn in school or finding the scientific literature. They're just making up bullshit to make themselves sound more intelligent or smarter, or sell some sort of product or whatever. But then we have animal trials and in vitro studies. We didn't talk about these. In vitro studies are things in a cell culture. We got cross-sectional studies. Now we're talking about humans. Case control studies where we sort of isolate two different populations of people and compare one to another. So different populations of people in different countries, or people with the same. Look at Japanese people who have grown up, first generation. They grew up in the U.S. eating a U.S. diet versus Japanese people who are living in Japan. What's the impact on cardiovascular disease, for instance? And there's cohort studies. You follow people, the Framingham study, that sort of thing, where you follow cohorts of people and watch what happens to cardiovascular risk, watch what happens to various things. How important is exercise over the lifespan in terms of preventing the risk of hip fractures in women, something like that, right? What kind of exercise? Then we have our randomized controlled trials, placebo-controlled, double-blinded, all of those are important. And then you usually see at the tip top here the meta-analyses and the systemic reviews. And I do think these are obviously super important. And the thing that I come back to is that these are telling us about what the kind of the purpose of science is can we take a phenomenon studied in a population, which we know is relatively homogeneous, and say with statistical reasonable probability that if we give this supplement or we have this condition, that we're going to have this particular effect or this particular outcome or this elevated risk factor, what have you, under those circumstances. And that's something that basically reflects the generalizability with which that comes from the science, that we're going to see this particular effect. This thing's going to happen. Okay, so we know you could look at a meta-analysis that says resistance training increases muscle growth, right? By whatever. And you see that's a statistically significant finding, and we see that over the studies, and we see that in reviews and what have you. But there are some people who are non-responders, right? Yeah. And there are some people who are hyper-responders. So these individual randomized controlled studies where you see the individual data, and I talked about this here, and I talked about this in my Why You Don't Look Like a Pro talk. The variability is important. We can see that in these studies, depending on how they report the data. And we can even see that here in these case control reports. We can see this in individuals. And any coaches out there, Scott, you know this as well as anybody, not all your clients are the same, right?
Yeah.
Some of them, like, let's say whatever, trenbolone is God's, it's the holy grail, right? It works great. And other people, nope, just fucks them up because they can't sleep, they can't recover, and they don't go anywhere.
Right.
So you've got these situations. So this is the hierarchy of scientific evidence, but there are also other ways of knowing things. So that's important to keep in mind. There's the ethical issues, animals versus humans. Tests of adverse outcomes, like the LD50s, like what kind of a dose does it take to kill off 50% of a test population or test sample? We're not going to do that in humans, right? Mentioned muscle excision, taking out entire muscle mass, fiber counting. You can't do direct body composition in humans. You can do a DEXA, do those sorts of things, but you can't actually tell someone how much body fat they have unless you kill them and do a chemical analysis, and that's not worth it. And I mentioned this too, ease of data generation. You can bring animals in and do sorts of pilot studies, and you just get your subjects are right there. They're available. You just order them. Your animals show up they're delivered to your door. They're delivered to your university. You go pick them up. And you're good to go, right? And you can, and they're expendable to some degree. I hate this, but this is sort of how things work. You do have to get research. You'd have to get approval to do things in the university setting, the research setting.
Sure.
But humans require much more care and time dealing with human subjects. People that, are sort of keyboard scientists, warriors who say, oh, you didn't have enough people, or you had the huge dropout rate. It is not easy to recruit subjects. You deal with so much crazy stuff.
I bet.
Doing that. It's a massive output of energy, keeping people happy and motivating them, et cetera, et cetera. So you can get kind of a broad brush with the animal research. Some of it's applicable, some of it's not, depending on what you're studying. And you're getting more of the finer strokes on understanding these phenomena from human studies. And then you need to look at the individual data points. Look what happens to some people. Some people who recomp during studies, they go into training, they lose body fat, and they gain muscle mass. And other people don't gain any muscle mass. They go nowhere. So you're still not getting everything when you're looking at the statistical significance, using the statistical significance lens that is typically used in randomized, controlled, placebo-controlled, double-blinded studies, because there are differences among individuals, and that's what matters for you, is what works for you, even if the study says it doesn't or it does. So,
yeah.
Happy New Year! Say hello.
There's the whole crew, the whole pack.
Yeah, that's the Suki in the background. That's the Suki in the front here, little Sukaroo.
Yeah.
My Nugget,
Sukaroo.
And there's the Blitzy Boo, my Blitzy Bear, and this is the Foxy Owl.
Foxy in the back.
Little happy fox. Yep.
That's nice.
With the waggy tail, you can see.
Is that a new picture?
That's an older picture. I was looking. I'm using my laptop. I have a bunch of pictures on my other computer, but this was in our truck camper.
Oh.
This is right before the pandemic, actually, when I got stranded there for a couple of weeks.
Yeah. Well, they still look happy. They're still glad to be there with you.
Oh,
what are we doing today, Dad?
That was fun. Yeah. Exactly. Yep. So.
All right. Well, listen. If you were to sum this up, Scott, into the elevator pitch, are rat studies useless?
I froze up for a little while there. Sorry, I quit came out of PowerPoint. Can you hear me now?
I can hear you. Can you hear me all right?
Yep.
All right.
Only just a short blip. So the elevator pitch. How to summarize this? Yeah. Don't throw the baby out with the bathwater. Animal research. There's all sorts of utility for this. The things that just can't be done, and they give us insights that we otherwise couldn't have, like that phenomena of fibers being average size in muscles that are larger. You don't have hypertrophy, but you've got a larger muscle. So there's so much there, but you need to contextualize it. So there are times when the animal research is much less relevant, and there are times when it's very relevant, and it depends on what aspect, what feature of physiology, of adapt or response to topography that you're concerned with. And to generalize and just say that how do it was phrased? Animal studies don't apply to humans is just really an overgeneralization that is not true when stated in that fashion. There very well can be some cases when you can this one doesn't really fit. And some of that can be that the animal studies do apply to some humans, but they may not apply to you because you're an outlier in terms of that particular feature, in terms of that particular response or adaptation. So that's the thing to consider. And you can always just read the studies and make your own mind up, but just throw that away, you're missing out, Yeah. It's like you're like the guys I looked at 2 women and 2 guys that walked past my driveway and all women are taller than men. I'm never going to date because I want a woman that's shorter than me and they're all taller. It's like, oh my gosh, right? You've just lost your whole relationship possibilities because you didn't look a little bit closer into the data. And everyone has the ability to do that. You can find this stuff, as I say again and again, on Google Scholar, on PubMed. It's all available. It's so available. Now, it's amazing. So don't undervalue your own ability to scrutinize the research because average intelligence person can figure a lot of this stuff out if they're willing to try.
You know what? I should dig back, Scott, and see if I have the video still for the episode where you talked about learning how to read studies. I feel like we could re-release that same podcast because that was excellent. That was a good 2+ years ago now, maybe 4 years ago even, But I think that would be a good one. That would be a fun one to go back over again, just to talk about the basics about here's a study, here are the parts of a study. This is what you can do with it. I think that a lot of people would get a lot out of that.
Yeah, and I did that. That was a topic on I can't remember which one, other podcast that I did like in the last year.
Okay, yeah.
I've done that topic a few times.
Yeah.
This is a big one.
Yeah.
So it's out there. It's, you can lead the horse to water, but you can't make him drink type of thing.
Yeah. Yeah.
But maybe somebody will, it'll perk somebody up. The thing is, I think, and this is our both guests, we don't know, and I'm not going to call anybody out, but chances are, and this is the issue. This is kind of the crux of this, is that to some degree we have to sort of trust in someone, right? Someone's the expert, right? And you can't be an expert in everything. Like I always use an example, unless you're an auto mechanic yourself, you got to take your car to someone. Maybe you can change your own oil and you can, put new tires on or what have you. But eventually you're going to have to let someone else be your expert and make some decisions for you. And if your expert has told you something like, that animal studies, they don't matter whatsoever, that's the thing to kind of watch out for, because that may be very true in a very specific instance. But the thing I would suggest people to do is to ask that expert for the evidence for that. And if they are truly the expert and they come up with that because they have, a very deep insight into that particular area, then they should have that information on the top of their head. They should be able to give you an example or explain themselves really, really, really easily. The believe me just because I said so type of response is the one that's like, oh, okay. Yeah. Maybe I'll go look into it myself. It's kind of like when you go into the car, the mechanic, and they say they will give you this estimate. It's like, well, why do we got to do that? And their answer doesn't make sense. It's like, okay, trust your intuition. Yeah. And go get a second opinion. So second opinions are totally worth it in this area.
Yeah. And it's funny. That's the exact reason that you don't really like to be called Dr. Scott Stevenson, because I think a lot of people don't know that. You don't want people to put you on that pedestal of being just blindly trust. You would rather people ask those questions, which, I have a lot of respect for that.
Yeah. It's a weird thing. It's like the fan phenomenon, or it's nice. It's good to have respect for people, and it's good to know where they're coming from. Right. Yeah. But the doctor thing, it puts, I see this all the time. You've probably seen this with your clients. I see this with my clients and with friends who've gone in and they speak with Western physicians. And I'm not trying to bash on Western physicians, because just like with every profession, there's awesome trainers, there's awesome barbers, there's awesome nail technicians, there's awesome mechanics, and there's some that aren't so great, right? Yeah. And there's some physicians, and this happens just because we have a mindset in our society with Western physicians, and I think just the term doctor, that they have, MD stands for, the joke is minor deity, right? These are gods, and they aren't to be questioned. And some doctors, they don't want to answer those questions, and they can become very, some can, they just tell you, they will give you the answer to these things. Yeah. So that is it's a very generalized perspective that I've noticed, especially in that context with Western physicians and the doctor title, that it's just part of our unconsciousness, I think. And we tend to just, when you see the doctor thing, it's like, oh, okay, this person knows more than me, Yeah. And then they stop questioning that person. Like, no, that's like, it should be the opposite. I've said a million times. It's like, now you have a resource for information. Right. And if this person's going to be, is there a good teacher, which is hopefully why you're there to learn from them. Now you can ask them questions. They should be able to tell you all sorts of stuff. Not the opposite. Like, this just believe me thing. It's just the opposite of what it should be. It should be like, now I can pick your brain. Be nice. Don't come up to someone in the gym and start asking them questions, right? For half an hour. Yeah. But you've got a resource in the doctor person. But I avoid that just because most people who ask me stuff, they recognize that I can be a resource. And the doctor thing, generally, it ends up working against what I'm trying to work towards, which is openness of information and helping people learn for themselves.
Right. Well, with all that said, Scott, I appreciate you taking the time to go over all this. Like I said, man, this is something that I think you could specialize in this topic versus anybody else that we podcast with. So I'm grateful that we do have you as that resource.
Yeah, this is my gig, man. I look at the research and I try to make it understandable. So figuring out when I've talked about that, for instance, in the context of NSAIDs and various of my articles. Yeah, I've brought out that you don't always see the same responses or adaptations in humans versus rats. You got to be very careful about that. Yeah. There's numerous responses or numerous examples are popping in my head, but we'll save that. So there are many cases where I brought that to the forefront, and so there's some truth in that, but not a black and white world, baby. Yeah. Unfortunately.
All right, guys. Well, for another episode of Muscle Minds, go to byobbcoach.com. You can get Scott's book there, Be Your Own Bodybuilding Coach, or you can find it over on Amazon. It's a great book. You can get the hardcover on Amazon. You get the ebook at byobbcoach.com. Of course, go to our great sponsors, truenutrition.com. Use our code THINK. They're having a New Year's thing where they have like 15% off the site. So for our live people who are watching here on the Facebook group for Think Big Bodybuilding Media, go take advantage of that right now. Otherwise, use our code THINK. Helps to support our programming, and you get a small discount with that. Also, Strom Sports Nutrition for those of you in the UK. And, of course, supplementsource.ca for those of you in Canada. You get great deals that roll week to week. They change all the time. Of course, thank you to everybody on Patreon. Appreciate you guys very much. And thank you to everybody who's watching live today. And Scott Stevenson, most of all, thank you to you. It has been a pleasure to have another year of podcasting, and I look forward to seeing what we do in the future, man.
Hell yeah. 2000, someone who might listen to this, just going to laugh, but 2023 is our year, Scott. It's our year, baby.
Yeah, hopefully that doesn't come back to haunt us, right?
Right. All right. Don't speak too soon.
Somebody said that at the beginning of 2020 when the pandemic hit. It was right at the beginning of the year, and somebody paid for everybody's food at a restaurant, and they did like a news interview about it, and this woman was like, 2020 is going to be the greatest year ever. And then they kept replaying that clip throughout the whole year. Anyway, guys.
I saw something the other day too. And then I realized, this is in the context of the pandemic, that this year, 2022, is 2022.
Yeah, part
just
two.
Same shit all over again. Yeah. Oh, that's funny.
All right. See you guys.
Adios.